colors close to each other with a similar wavelength or frequency don't actually clash with each other. They look just fine. And that's because we don't measure wavelength or frequency with our eyes. We do measure frequencies with our ears instead. And so two sounds that are very close to one another sound really bad. If they're at a certain range of differences, they produce beats. And that's between approximately 0.1 hertz apart from each other up to 5 hertz. So to demonstrate this, I have two pretty nicely matched tuning forks that produce a 440 hertz frequency. So if I play the two simultaneously, you can see on the oscilloscope they superimpose the sound waves they produce that are picked up by this microphone and displayed on the oscilloscope, superimpose into a nice sine wave. And if I'm quiet, you can just see that the sine wave gently decays in amplitude, stays with the same frequency, and nothing too bad happens. Just gentle decay with time. If instead I mismatch these frequencies by a little bit, just a hertz or two, by adding weights on the tines of one of the tuning forks, but not the other, I'm going to place it about a third of the height, so I can still strike it with a mallet at the top and produce a sine wave with this. Another sine wave with the unaltered tuning fork. Now let me play the two at the same time and let's see what happens. As you can see on the oscilloscope, the amplitude goes crazy, it goes up and down, up and down, up and down. These are called beats. These two waves superimposing beat. That's a verb. The two beating waves actually go in and out of phase at a very small frequency. At the frequency, that's the difference of the two, about a hertz or two in this case. Let me do it again so you can watch it in this mode. On the oscilloscope, you can listen to it with your own ears because the microphone of this recording is actually picking up the difference. If I'm quiet, you can detect it. And finally, let me change the setting on the oscilloscope and show you what the beat envelope looks like. The amplitudes, as they go up and down, up and down, up and down, you can see on the oscilloscope, they go up and down, up and down, up and down, and you can see this beautiful envelope that goes to maximum and then zero, maximum and then zero, a very small frequency. At the beat frequency, that's approximately 1 or 2 hertz in this case. This doesn't happen at all if I repeat the experiment without these additional weights. So now the two frequencies are very, very similar to each other. And all we observe is a decay in time, which is expected. The frequency remains the same, the amplitude decays exponentially, and that's all we observe. No beats when the frequencies are well matched. Slight mismatch, beats. Thank you. I have two function generators, both of which are generating sinusoidal waves with 200 Hz frequencies. The superposition of the two is actually obtained by a mixer that's mixing the two, adding up the two, superimposing the two, and sending the signal to the oscilloscope. If I turn one of them off, the one that you see on the display here, You can see that the other is still there, exactly 200 Hertz. You can still see it on the oscilloscope. If I switch on the previous one, you actually have the two and the superposition of the two, and you can see that the wave has a greater amplitude. Great. So what happens if I slightly mismatch the frequencies of these two function generators? I'm going to try by say a 5 Hertz amount. I'm going to plug in the number 205, and you can clearly hear beats. You can also watch the amplitude oscillate on the oscilloscope, and if I change setting on the oscilloscope, you can actually see the beats directly. You can see that the amplitude goes up and down, up and down, up and down, and that's classic beats. If I go to less, maybe 204, the beats are still audible. You can see that they're less frequent, therefore their difference is only 4. So the frequency of the beats is the difference of the two frequencies, so in this case 4 Hertz. 3 Hertz beat frequency, 2 Hertz, 1 Hertz. Can we hear beats? Can we see beats on the oscilloscope with even less than 1 Hertz? The answer is yes. Now we have 0.6 Hertz, 0.5 Hertz. Let's see 0.2. Obviously the frequency is very low. We can see on the oscilloscope this beautiful, very low frequency increase and decrease of volume or amplitude of the wave and loudness that we perceive with our ears. And if I go down to even 0.1 Hertz, we can still hear and measure with the oscilloscope very distinct beats. Very low frequency beats, fantastically interesting. On the high end, at what frequency do beats start to not be perceptible anymore? Well, that changes from person to person, but typically between somewhere around 0 or 0.1 Hertz and 5 Hertz difference, you produce beats. Between 5 and 10 or 20 Hertz difference of the two frequencies, you produce dissonance or roughness. Although the oscilloscope is still able to pick up variations. Let's try. Let's try going to 205 quickly and go up to 206. Still clearly see beats and can hear them a little bit. Maybe some of you can, some of you can't. 4 Hertz difference, sorry, 9 Hertz difference. 10. 15 Hertz difference between the two frequencies, and now it's very hard to see them as beats, to hear them as beats, to see them as beats on the oscilloscope, but we do have this perception of roughness of the sound that we hear because our neurons cannot tell apart these two frequencies. Thank you.